Good morning, dear students. Welcome to another session of microwave and antennas. So, in previous session, we started our discussion with strip lines, in which we discussed basics regarding the strip lines. That is, what is its schematic representation and how are the field lines associated. And along with that, we discussed another point: how we represent the microstrip line in the wire over ground representation. So in this case, and we observed a few more aspects related to this. That is, using the comparative method, we try to see what is the characteristic impedance of a micro strip line. So that is what we had discussed in the previous session. So this is the characteristic impedance of the micro strip line, but in this case, this is for the wire over the ground. Then if I have to approximate the same equation to the microstrip line, then we had considered a few parameters over here, and then we had seen what is the effective relative permittivity, and then we also had seen what is the relation between the diameter of the wire over ground and the thickness and the width of the strip line, thickness of the strip line and the width of the strip line. So based on this, we had the discussion. So when we substituted the equation in Z naught, we obtained this equation, that is equation 11.1.7, in which we saw the condition in under which we apply this is H is much lesser than 0.8 times W. So that is what we observed. So in this case, if you just observe, it is H is much greater than the diameter, that is D value. Diameter is related to this and H is there. But what about in terminologies of these parameters? So when we substituted, we obtained this representation wherein Z naught is given by 87 divided by the square root of epsilon r plus 1.41 ln 5.98 H divided by 0.8 W plus T. So these are the aspects which we had discussed in the previous session. Okay. And another equation what we had seen was Z naught in terms of mu, epsilon, H and W. So these were the equations what we had discussed. So that is in previous this thing, if you just observe. So here Z naught is also represented for a wide strip line. For a wide strip line, Z naught is given by H divided by W into square root of mu by epsilon. But this I can replace it with mu naught into mu r divided by epsilon naught into epsilon r. And when I consider mu r, that is relative permeability, as 1, then mu naught and epsilon naught, when I substitute, it is nothing but the intrinsic impedance in the vacuum. So it is 377 ohms or 120 pi ohms. So when I make the substitution and simplify the equation, this is what I'll be getting. That is Z naught is 377 divided by square root of epsilon r into H by W. So this is the equation what we will obtain. So based on this, we can see the problems. So we can observe one problem here. You need to obtain the characteristic impedance of the micro strip line for the parameters what are specified over here. So they have specified that relative permittivity is 5.23. The height of the substrate is 7 millimeters. Thickness is 2.8 millimeters and W is 10 millimeters. So these parameters he has given, and you have to identify Z naught. And in previous equation, since we have observed that what is Z naught, first we have to just check out what is the relation between H and W, and then we can look forward which equation we can apply. So in this case, this holds true. So we will be utilizing this equation. So when we utilize this, so we can observe When we substitute the parameters, the characteristic impedance turns around 45.78. That is, we substitute these parameters. Since all the units are in mils, so no need to worry, because in substitution all the units gets cancelled. If there are some changes, then you have to make the adjustments of the units which are represented over there. So in this case, when we substitute, we obtain Z0 equal to 45.78 ohms. So next discussion what we have is what are the losses which are present in the microstrip lines. So whenever we are talking of losses, right, there are three type of losses in microstrip lines. One loss is due to the dielectric substrate which is present. Another loss is due to the conducting element of this microstrip, that is say the strip conductor. Then apart from this, since we had seen that there are electric and magnetic fields associated with this when say current is passing through this stripline conductor, then what happens is that gives rise to what is termed as radiation loss. So totally three types of losses we can observe in a microstrip line. So the one is due to the loss due to the dielectric substrate, one is loss due to the conductor, stripline conductor, and the another one is the radiation losses. So these are the three losses which we can observe in a microstrip line. So generally we have seen that what is power specified as? Power is specified as V into I, where I is a complex conjugate in this case, because in previous session, if you remember, when we were deriving the transmission line equations, in those we could observe that V and I are involving the complex parameters. So we have to consider those parameters. And here what we are considering is we'll be considering the average power. So when we're considering the average power, it is V into I star divided by 2. So now when we substitute V parameter over here, Vi parameter over here, based on the previous analysis, so what we'll be having is we'll be reducing the equation to the incident parameter, that is V and I when I consider. And here you can observe that this strip line, micro strip line is placed along the Z axis. So based on that, you have attenuation which is present along the Z axis. So if you remember, we had utilized or represented the incident, the reflected voltage and current parameters. So based on that, we are considering this. So based on the power specification, if we just observe in terms of incident parameters, it will be V plus, that is the incident voltage, into e raised to minus alpha z. This indicates that it is in the positive z direction. It is measured along the positive z direction, and the I parameter is replaced with I plus into e raised to minus alpha z. So this is again associated with the incident current, and we had seen that the voltage and current actually are out of phase with respect to each other. So that is another observation what we had seen in the previous session. So based on that, we refer to this equation, that is V and I when I substitute, that is I complex when I substitute, I'll be having this equation, that is V plus into e raised to minus alpha z into I plus into e raised to minus alpha z divided by 2. So when we simplify this parameter, what we'll be having is since I plus, again if you remember, we had obtained an equation for z naught in terms of incident and incident voltage and incident current. We had obtained an equation in the previous sessions. So based on that, when you substitute this equation, right, that is I plus is V plus divided by Z naught. It is V plus divided by Z naught. So when we consider that, we can simplify this power representation as half into V plus square. So we'll be considering, say, the magnitude in this case, since they have separated the parameters of the exponential. So here we can just consider the magnitude of V plus, that is the incident voltage, its square divided by Z naught into e raised to minus 2 times alpha z. So when you simplify, this part we are representing as, say, P naught, and this one is e raised to minus 2 times alpha z. So this is giving you the phase representation. This is giving you the magnitude representation. So now when we consider P naught, right, it is nothing but the power which is measured at z equal to 0. That is what you are considering. So this parameter gives you the value of the power when z is equal to 0. So when you substitute z equal to 0, you can just see that this equation, this part turns to 1, and because of which only P naught remains. So this is the representation of the power. So now how do I obtain the loss factor? So when we are considering the losses, right, it is nothing but the attenuations what we have to consider. Based on that, we have attenuation constant alpha, which is defined with the help of this power specification. That is, it is represented in this form. That is, alpha is minus dp by dz. That is a differentiation of the power with respect to z divided by 2 times p of z. So here this attenuation constant will include two parameters. One is attenuation due to the dielectric constant, and the other is the attenuation due to the conducting element. So which we term as the ohmic losses, which are due to the skin effect. So that is what we will be just observing. So alpha is given in this equation. So when we try to estimate what is dp by dz from this equation, dp by dz from this equation, it turns around that is when we simplify this equation, right, it will be providing us with this simplified equation, which is half into magnitude of I square into r plus half into magnitude of v square into sigma. Now here you can see that this is a resistive component. This is the conductivity component, which is actually associated with the dielectric substrate. So whenever you take the differentiation, do the substitutions and simplify these equations, right, you will end up with this equation in which you have one component associated with the resistance and the other component associated with the conductivity of the dielectric substrate. So due to which what happens is this parameter is associated with the power, that is power which is basically due to the conducting element, that is the ohmic element, that is this conductor. And next one, this parameter is basically the power which is due to the dielectric material which is being used. So this differentiation leads to PC plus PD. That is the two. It is the sum of the two power components which is associated with the conducting strip line and the dielectric material. So now, based on this, if you just make the observation with respect to this parameter, where alpha is equal to dp by dz divided by 2 times pz. So when I just substitute it over here, what we'll have is, so if I substitute it, what I'll be having is pc plus pd divided by 2 times pz. So denominator is common. So if I just remove the denominator as common, then what I'll be having, so that is in this case, if I just substitute, what I'll be having, I'll be having pc plus pd, which is divided by 2 times p of z. So pc by 2 times p of z plus pd by 2 times p of z. So and when I equate these parameters, right, therefore in that case what will be happening, I'll be having alpha d, which is given by p of d divided by 2 times pz, and alpha c, which is given by pc divided by 2 times p of z. So these are again measured in Napier per centimeter. These are measured in Napier per centimeter. So this is the attenuations which are due to the dielectric material and the conducting strip line. So next one, we have the dielectric losses. Anyways, we have identified the dielectric loss alpha C. So in apart from alpha D, Apart from this, based on some previous equations, we can observe that what is the dielectric loss alpha d, which is given in terms of the conductivity, the permeability and permittivity. So it is equal to this equation, that is alpha d is equal to sigma by 2 square root of mu by epsilon. Then we have another parameter, that is the theta specification, wherein we use this representation, that is tan theta is given by sigma by omega e. So now when we substitute when we substitute these parameters in this equation and try to simplify it, we obtain alpha d in terms of omega mu and epsilon. Omega mu and epsilon, and the theta specification. Again, theta specification is including all these parameters: conductivity, the frequency in terms of radians, then the permittivity. So in previous case, we are just specifying it in terms of the power representations. But in this case, what we are doing is we are representing it in terms of the conductivity of the dielectric material, permeability and permittivity. So these specifications we are trying to obtain the representation. So when we obtain alpha d and simplify it, it will be given as omega by 2 square root of mu into epsilon into tan theta. Again, this is given in Napier per centimeter. So based on a few of the reference to the papers or the books, the equation what we have seen can still be simplified in terms of the filling factor, that is the dielectric filling factor, what we specify as this equation. So in which alpha is specified in terms of dielectric filling factor. Now here you can see that it is just specified as epsilon. But when we considered in previous case, we were referring to the effective relative permittivity. Here it is just the permittivity. Here we are referring to the effective relative permittivity. So when we consider this, the alpha d value, that is dielectric loss, will be given by this equation, that is 4.34 into q into sigma divided by square root of epsilon re into square root of mu naught into u naught by epsilon naught. And if we still further simplify this, this is the equation what we'll be obtaining. Now here in this case, the q what we are specifying over here, it is actually relevant to the effective relative permittivity, which is termed as the dielectric filling constant. The effective here we can see that the dielectric filling constant is given by epsilon re minus 1 divided by epsilon r minus 1. So these are the parameters which we have utilized in order to represent the alpha d value. Now, when we still further simplify the equation in terms of, say, per wavelength, here if you just observe this one, if you just observe, this is in terms of dB per centimeter. It is specified in dB per centimeter. But if I want to specify it in terms of the guide wavelength, or the wavelength in short, so it will be given by this equation, which is 27.3 q into epsilon r divided by epsilon re into tan theta divided by lambda g. So when you're utilizing this equation will be giving you the result in terms of dB per lambda, that is lambda g, which is specified over here. So this lambda g generally was specified as the guide wavelength. So this lambda g is equal to lambda naught divided by square root of effective relative permittivity, where lambda naught is actually the characteristic wavelength, that is wavelength in the free space. So when we want to specify say lambda g in terms of the frequency, we can substitute lambda naught as c by f and obtain this representation. So this is lambda g representation which is being utilized in this equation. So this is the dielectric loss what we have specified. So here we specified it in terms of the power specification. Here we are specifying it in terms of the conductivity, permeability, and permittivity. So these parameters we are specifying. Then along with that, other representation is in terms of the wavelength and making use of the dielectric filling factor. So these are the aspects related to the dielectric losses. So then what about the ohmic losses? So in previous this thing you saw that the again ohmic losses were specified in terms of the conductor losses, that is in terms of the power. Now here when we are considering say the electric and magnetic field, we have to deal with the say discontinuities, we have to deal with the boundary conditions, and we have to deal when boundary conditions come into play, then we have to deal with say conducting materials. When it comes there, we have to deal with what is termed as the skin effect. So based on that, we can represent the conducting loss or the ohmic loss as alpha c equal to 8.686 into rs divided by z naught into w, and this is specified in terms of dB per centimeter. So which will be in which w by h is greater than 1. So this is this equation holds when this is the condition. Now here, what is rs? Z naught is anyways the characteristic impedance what we have seen. W is the width of the strip line and h is the height of the dielectric material which is being utilized, and rs is the skin resistance what they specify. So what is basically the skin resistance? In this case, again, it is given with respect to the skin depth. So here you can see that what is skin resistance? It is square root of pi into f mu divided by sigma. So which is actually the skin resistance, and it is given in terms of ohm per square. So if I specify it in terms of skin depth delta, it will be given as 1 by delta into sigma, where delta is equal to what? Delta is the skin depth, and it is given by 1 by square root of pi f mu into sigma. Pi f mu into sigma, and the skin depth, when we are utilizing these parameters, it will be given in terms of centimeter. So these are the specifications for the ohmic losses, which is given in terms of rs, that is the skin resistance, surface skin resistance. Next comes the radiation losses. So whenever we are talking of transmission lines which are making use of high frequency waves, electric and magnetic waves are associated with that, due to which we can see that it also helps in the radiation. And these radiation lead to some of the losses. These losses are due to what? Due to several discontinuities which are present. And these several discontinuities, what they look, it is because of these approximations what we are observing. One is the transverse electromagnetic transmission. Then the due to the dielectric material, that is what is present or what has been utilized in building the say the microstrip. Then apart from that, when we are making some assumptions, right, we also look forward to neglect the transverse electric field components. That is we had seen previously, right? So if you observe this, these field lines are actually at say 90 degrees with respect to this say the strip line. So the strip line, when we consider, they are almost at transverse directions. So we are making some assumptions also or approximations because of those. So because of these factors, right, what happens is we will be observing some of the radiation losses which we see when the strip line is used for say as a transmission line over there. Then apart from that, the thickness what we are considering also matters. So these are the few of the aspects which lead to the losses due to the radiation. So these are a few specifications pertaining to pertaining to the losses which we observe in the strip lines. So then apart from that, what are the quality factor of the microstrip line? So whenever we are observing the quality factor, we have to look forward for the resonant circuits. So here, since we require very high quality for the resonant circuits, because in many of the microwave integrated circuits, that is the requirement. So what is the quality factor associated with these strip lines? So again, it is dependent on the previous discussions what we have done. So here we have again two kinds of specifications for the quality factor. One is due to the conducting material and the other one is due to the dielectric material. So if I come down directly to this equation, so here we can see that quality factor which is associated with the attenuation constant related to the conductor, it is given by QC, which is equal to 27.3 divided by alpha C. And we had seen that where alpha C is 8.686 RS divided by Z naught into omega. And Z naught was previously we had observed wherein we consider that W is greater than H. So if this is the case, then we make use of this equation. So based on those specifications and what you're utilizing, so here you can see that alpha C, if it is specified in dB per wavelength, then what was the equation? If you just observe the previous case, so here we can observe sorry it isn't specified over there. This should be dB per say centimeter. If I'm making use of this equation, it will be dB per centimeter. But if you're representing the same equation in terms of dB per lambda, that is, you have to make some adjustments over there. You have to substitute the parameters. So when you substitute those parameters, when you simplify the QC for the white strip, that is W is much greater than H. So then the quality factor for the conductor, this thing turns out to be 39.5 into H by RS. So that is this is when alpha C is dB per centimeter, and this equation is when you specify alpha C in terms of dB per lambda g. So based on that, these are the two representations what we'll be having. Then when we make the substitution for the RS specification, when we make this substitution, we can see that on simplifying, the quality factor turns out to be 0.63 times H into square root of sigma into F. And the frequency what you're specifying is in terms of gigahertz. So here, for example, if the frequency is 2 gigahertz, so here I'll be just using the value of 2. This has to be specified in gigahertz, and here I'll be substituting the value of F in terms of gigahertz. So if it is say 3.1 into 10 raised to 9, this is hertz. So here if you just observe, this is nothing but 3.1, this is 10 raised to 9 is giga, so this is 3.1 gigahertz. So what I'll be doing is I'll be just substituting 3.1 over here. So you have to specify F in terms of gigahertz in this equation. So here what you have specified, quality factor, which is 27.3 divided by alpha C, wherein alpha C is specified as dB per centimeter. And if it is specified as dB per wavelength, then QC is given by this equation. And lastly, if you substitute for RS, right, you will be getting QC, which is represented by this equation 11.1.36. Now comes the another quality factor specification, which is due to the dielectric attenuation. So which is given by QD, which is given as 27.3 0.3 divided by alpha d, and again remember alpha d is specified as dB per centimeter. So this equation holds when alpha d is specified as in terms of dB per centimeter. If we specify it in terms of lambda g and make the substitution, right, we obtain qd is equal to 1 by tan theta. So we obtain this equation in terms of theta representation, which is given by 1 by tan theta. So these are sorry, it got disconnected. So this is the quality factor specification when we are looking forward with respect to the conductor and the dielectric constants. So in short, QC is 27.3 divided by alpha C, and QD is 27.3 divided by alpha D. And if you want, you can make the necessary adjustments in these equations and obtain the relevant parameters. So along with this, let us solve another problem. We saw one problem in from Samuel Leo. So another problem which is based on identifying Z naught. So here we have calculate the characteristic impedance. Calculate the characteristic impedance, that is Z naught, for the microstrip line, given that the thickness of the dielectric substrate is 175 microns. So thickness of the dielectric substrate, then thickness of the strip is 70 microns and its width is 250 microns. The dielectric constant of the material is given as 4.5. So here be careful when you're reading the terminologies here over in this case. So you have to identify Z naught for this material, what is being specified for the microstrip line. So in this, if you just go through this, this is the thickness of the dielectric substrate. So if you just observe here, so if I make an observation over here, this is the dielectric substrate. The thickness of this substrate is specified in this problem. So thickness is specified as 175 microns. So here this thickness, what they are specifying is nothing but the parameter h, that is the height of this dielectric. So this 175 micron is actually h value, h is equal to 175. Then you come to the thickness of the strip line. So in this case, thickness of the strip line, so which is T, that is, this is the thickness of the strip line, which is T, which is 70 microns. And then what is the width? What is the width? Width is 250 microns of the microns for the microstrip line. And he has specified that the dielectric constant of the material is 4.5. So this is actually epsilon r and not the effective relative dielectric constant. It is just the epsilon r. Now here we make one check whether h is less than 0.8 times w. So here if you just see h is 175 microns and 0.8 times w, that is 250. When you just consider, it is 200. Therefore h is less than 0.8 times the width of the strip. So because of this, what we can do is we can make use of the equation wherein we substitute for the d value and we substitute for the effective dielectric constant. When we make the simplification, what we have 87 divided by square root of epsilon r plus 1.41 ln, that is the natural log of 5.98 into h divided by 0.8 times w plus t. So when we substitute the parameters, all the parameters are known over here. When we substitute these parameters, we will obtain Z naught as 48.29 ohms. So this is what we are obtaining for the Z naught value. So again, we had seen these equations. So these are the simplified parameters. Here directly they had taken it. So these are the simplified parameters. QC, QD, what they had specified, right? When you simplify these are the equations what we'll be getting. So when you make the adjustments and obtain the value in terms of lambda j and substitute it, you'll be getting the QC values and QD values. So based on these things, we can look forward for another problem. A microstrip line is composed of negligible thickness copper conductors mounted on a dielectric substrate of thickness 1.4 millimeter. Loss tangent, that is the theta value, is 4.4 into 10 raised to minus 3. So this is in terms of radians. This is in terms of loss tangent. It is specified directly. It is the loss tangent, which is 4 into 10 raised to minus 3. Then we have the dielectric constant, which is say 9.6. The width of the microstrip line, that is W, is 3 millimeter, and it is operated at a frequency of 10 gigahertz. So we need to determine few of the parameters, that is characteristic impedance, effective relative dielectric constant, then the loss due to the dielectric, loss due to the conductor, that is the attenuation factors for both the cases. Then we need to look out for radiation loss if the dissipated power is 4 milliwatt into the okay, I'll just check out with this value. It is 4 milliwatt at present. Then the quality factor QD and the quality factor QC. So based on these parameters, we can see what values are being specified over here. So first one, the thickness, dielectric substrates thickness. So this is nothing but the H value, which is 1.4 millimeter. Then you have the loss tangent, that is the direct value of tan theta. You have the loss tangent, which is the direct value of the uh, say tan theta. This is not the radians. That rectification you please make. It is a loss tangent, that is tan theta, what is being specified, which is 4 into 10 raised to minus 4. Then epsilon r is 9.6. Width is given as 3 millimeter. F is 10 gigahertz, and P is 4 milliwatt. That is a pre-transmitted is 4 milliwatt, and sigma value is given as 5.8 into 10 raised to 7 mho per centimeter. Now, based on this value, right, you just make the adjustment. See that all the units are in proper form. So if it is in millimeter, see that everything is in millimeter. If it is centimeter, make it in centimeter. If you are using the specifications as dB per centimeter, so all these representations should be in terms of centimeter. So we had seen previously, right? So we have seen that it is dB per centimeter if I'm using this equation. So just take care of those things. That is, whatever values are there, you specify it in terms of centimeters and use only this value. No need to simplify and write it as 0.14 into 10 raised to minus 2. So we'll just be utilizing these values, represent this in proper form, and then we will go ahead. So because of that, these values are represented in centimeters. So 1.4 millimeter is 0.14 centimeter, and 3 millimeter is 0.3 centimeter. And this is already specified in centimeter sigma value. So now Z0, if you have to identify, say based on the W and H values, whether W is greater than H. So if you just see 0.3 is greater than 0.14. So that equation holds true, because of which you make use of the other equation, the second equation what we had represented. So here when we consider that Z0 is equal to 377 divided by square root of epsilon r into h by w. So when we substitute the known values in this, so we'll be getting Z0 equal to 56.78 ohms. Then epsilon re, which is given by 0.475 times epsilon r plus 0.67. So when we substitute epsilon r and simplify it, we get effective relative dielectric constant approximately around 5.2. Then what is the other thing he has specified? Mm, he has specified to identify alpha d, alpha c, these factors. So if you want to identify what is alpha d or alpha c, right, we make use of this equation, that is, this is given in terms of lambda g, that is dB per wavelength. It is dB per wavelength. But when you substitute these values, right, what happens is all the representations will be in terms of, it will be in terms of centimeters. So therefore, when you simplify it, you will be getting it in terms of dB per centimeter. So here we have alpha d, which is 2.73 into q into epsilon r divided by epsilon re into tan theta divided by lambda g. So this lambda g can be obtained from the given frequency. And we consider the speed of the wave as c, which is 3 into 10 raised to 8 meters per second. So when we obtain that, when we simplify it, that is, this is the equation what we are utilizing. So when we utilize this equation, we'll get 1.3118 centimeter. So when we substitute these parameters, we'll get the attenuation due to the dielectric as 7.5 into 10 raised to minus 3 dB per centimeter. Now similarly, alpha c in terms of RS. So let us see what we'll be having. So it is 8.686 divided by Z naught into W naught. This is the skin resistance. And for skin resistance, you have seen that it is square root of pi into mu into sigma divided by, or it is 1 divided by delta into sigma, where delta is 1 divided by square root of mu pi f, pi into mu f sigma, pi into mu f sigma. So when you so for that case, you can make use of the loss tangent equation, since a few of the parameters are not specified over there. So in that case, what we can do is we can make use of the loss tangent equation and obtain the values which are required. And based on those equations, we'll be getting the quality factor with respect to the dielectric constant. That is, we have sorry we want to obtain this. So you can obtain it either using this parameter, but again you have to convert it into the dB per lambda g specification. So that specification, if you convert, then you can use it directly, or else you have to estimate these specifications and obtain QD, which is 2768.25. Similarly, for QC, when you obtain, you get it around 67.17 microns. You'll be getting it in these terms. So this is with respect to the strip lines, microstrip lines and the strip lines. So next we'll be going ahead with the parallel strip lines. So in coming 4 sessions, we'll be discussing regarding these parameters.